In the last video, we were introduced to enolates, and we said that we could create and isolate those enolates by treating either our aldehyde or our ketone or our enol with a strong base. Well, choosing the right base takes a little bit of consideration, so that's what we're going to talk about in this video. So one of the first things we have to consider when choosing a base is the base needs to be strong enough. So most aldehydes and ketones have pKa's in the range of 16 to 20. And so we need to choose a base that's strong enough to deprotonate these alpha carbons. So when the basicity of the base that we're using and the enolate are similar, and so really for that I should be talking about the pKb values of the enolate and the base are similar, we have significant amounts of both reactants and products present in the reaction mixture. And so we can think about the stability or the pKb's of the base and the enolate, or we can also look at the pKa's of the aldehyde, ketone, enol, and the conjugate acid of the base that we're using. And so whichever one we look at, in this case the pKa of our aldehyde in this case is similar to the pKa of ethanol, which is the conjugate acid of the base that we're trying to use. And so in general, sodium ethoxide or sodium methoxide or sodium hydroxide are not strong enough bases to make the equilibrium favor the enolate. And the reason this can be a problem, if I have significant amounts of both the aldehyde in this case and the enolate, these two compounds can react with one another. Sometimes that's desirable, sometimes it's not. The reason they can react is because the enolate is a strong nucleophile, the carbon of the carbonyl group is a strong electrophile, and so these two can react with one another. Alright, so if I want the equilibrium to favor the enolate, I basically need to use a stronger base. And so this slide has two popular options. The first one is sodium hydride. And this is useful for a couple reasons. A, hydride is a much stronger base than hydroxide or ethoxide or methoxide, right? The pKa of H2 is 35, right? And so the equilibrium is going to favor the side that has the weaker acid or the weaker base. Those sides will be the same, right? And so because the pKa of H2 is much bigger than the pKa of this aldehyde, the equilibrium is going to favor the products. Another advantage of using sodium hydride is that after the hydride deprotonates the aldehyde, it's going to produce H2 gas, which is going to bubble out of the solution. So this conjugate acid is not even going to be there for the reaction to go the other way. So sodium hydride is a convenient choice for forcing the equilibrium to favor the enolate. Another common choice is LDA, or lithium diisopropyl amide. This compound is a strong enough base to deprotonate our aldehydes or our ketones. So LDA is a strong enough base that it will force the equilibrium to favor our enolate. And if we compare the pKa's of our typical aldehyde with the pKa of the conjugate acid of LDA, we can see the pKa of the conjugate acid of LDA is much higher than the pKa of the aldehyde. So the side that's the stronger acid will force the equilibrium to the other side and will favor the enolate when we use LDA as a strong base. Now here's an example where I have a diketone where I don't have to use a base as strong as LDA or sodium hydride. And we saw this compound last time. And when we saw this compound in the last video, this was one of the cases where the enol was actually more stable than the diketone. The reason being the enol had conjugation, so resonance stabilization, and an intramolecular hydrogen bond. And this compound is also unique in that we don't need such a strong base. It is much more acidic than your typical aldehyde or ketone. The reason being, when I pull off one of these hydrogens, it's going to be doubly resonance stabilized. And so I can draw resonance structures where the negative charge is localized on both of these oxygen atoms. And so because this anion is particularly stable due to these two different resonance structures where I can delocalize that negative charge on these two different oxygen atoms, this makes this conjugate base very stable, making the conjugate acid particularly acidic, and so I don't need a very strong base to deprotonate it. All right, so unlike our sort of ordinary aldehyde that was with our first examples, I could use sodium ethoxide to deprotonate this diketone. All right, so to kind of summarize, it is important to know what base to use in order to generate the desired result. If I use a weaker base, like sodium hydroxide or sodium ethoxide, and I treat most ordinary aldehydes and ketones, I'm going to form both the enolate and the ketone at equilibrium. Now, sometimes this is desirable, and so we may want to do this. However, if I only want to have the enolate, I need to go with a stronger base. On the other hand, when we have these diketones, where they're separated by just a single carbon atom, they are much more acidic than our regular aldehydes and ketones, and so even a moderately strong base will give us almost all enolate when we're at equilibrium.